You can fill in your notes over Newton's third law of motion to help you fill out your handout. So what is Newton's third law? Well, it basically says whenever an object exerts a force on a second object, the second object will exert an equal and opposite force on the first object. You'll also hear it this way. For every action, there is an equal and opposite reaction. Now, those two forces are called either action forces or reaction forces, and they're always paired. So they're always going to be paired up. So, one way to say it is A exerts a force on B, B exerts the same force on A. An example of this would be a swimmer pushing on the water and the water pushing on the swimmer. So, if I just drew a quick example of that, I have some water right here. Okay, put a swimmer in there, or at least a swimmer's hand. Here's my swimmer. Okay, and what it's saying is the swimmer is going to exert a force on the water. Well, let's make sure we kind of know what direction my swimmer's going. We'll make him go in this direction. And his feet somewhere back here. So the swimmer is going to push on the water, and according to Newton's third law of motion, the water is going to push on the swimmer. Okay? So for every action there is an equal and opposite reaction. So for example, if I made up a number, this might be 10 newtons, therefore this has to be 10 newtons. Now, at first glance, it might actually appear then, you might ask yourself, well, why don't all forces cancel each other? And the secret to that answer, I'm going to try to diagram with you and help you understand that on the next page. All right, we got ourselves a little situation here where we have Big Bad Billy and we have Little Leroy. And we have a box that's sitting still, and they decide to each push on the box. So I'm going to try to show you how this situation can both represent Newton's third law of motion, but we'll also explain how even though it looks like forces cancel out, they really don't cancel out. So, or at least they don't always cancel out. So let me see if I can go through that with you. So let's draw an arrow representing Big Bad Billy. So Big Bad Billy is going to push on the box, and I'll just put Big Bad Billy. Let's make up a number. Let's say he pushes with 100 newtons of force on the box. All right, you just learned Newton's third law. What's his third law state? For every action there's an equal and opposite reaction. So that means that the box is going to push back on Big Bad Billy, and it's going to push with the exact same force. So those two arrows represent Newton's third law being observed. But here's the deal. These two forces are not acting on the same object. This force is acting on the box, and this force is acting on Big Bad Billy. So if there were no other forces involved, that's an if, no friction or anything like that, if there were no other forces involved, what would happen is the box would accelerate this way and Big Bad Billy would accelerate that way. Okay? So these don't cancel because they're not acting on the same thing. They're acting on two different objects. This one acts on the box, this one acts on Billy. So I personally think it even gets clearer if you throw in a second little person over here, Little Leroy, to help explain the concept. So let's say Little Leroy pushes also at the same time as, I'll call him as Dad does. So this arrow represents Little Leroy pushing on the box, and let's just say he can only push with 10 newtons. And you understand Newton's third law, so you're going to end up with the box pushing back on little Leroy, and it's going to push back with 10 newtons. So, again, this follows Newton's third law. But going beyond Newton's third law, we can talk about what happens to the box. What is going to happen to the box itself? So, we're not going to care about any other things but the box. I heart the box. So I love the box. I don't care about what happens to Big Bad Billy or Little Leroy. Just want to talk about the box. So, to figure out if the box accelerates or not, you have to look at the forces acting on the box. This force is the box pushing on Big Bad Billy. So, it's not acting on the box. This is acting on the box. The force of Big Bad Billy pushing on the box, this force is acting on the box. This force right here is acting on the box, but this one's acting on little Leroy. So for the sake of illustration, the forces are still there, but for the sake of illustration, let's just cross out the forces that are not acting on the box. This force is acting on little Leroy. This force is the box acting on Big Bad Billy. And now I'm left with these two things acting on the box. So, what happens to my box? Well, slide that up just a little bit. There is a net force of 90 newtons, because you have to subtract 100 minus 10, of 90 newtons pushing on the box to the right, so the box will accelerate to the right. Okay, one more attempt to understand how things can accelerate and yet Newton's third law is being observed. So, what I have is a little soccer ball here, and a guy that's going to kick the soccer ball. So he kicks the soccer ball, and what happens? Well, we have the force of the guy, or the force of the foot, pushing on the soccer ball. Let's call it, just keep numbers simple again, let's call it 10 newtons. Newton says for every action there's an equal and opposite reaction. So that must mean there's 10 newtons pushing back this direction on his foot. Alright, those two forces are equal and opposite. Now, if this happened in outer space and there was no friction, what would happen? Well, if there were no other forces, he would accelerate this way, and the ball would accelerate this way. He has more mass, so he wouldn't accelerate as fast. This has less mass, so it would accelerate faster, but they'd both accelerate because there would be no other forces. It's an illustration how forces are always equal and opposite. Okay? Now, the reality is, when you kick a soccer ball, you don't find yourself flying backwards across the field. And here's why. That's because you're usually standing on the ground, or the grass, and there is static friction underneath of your foot. So when you want to move this way or accelerate this way, there's another force acting on you called static friction, and that static friction is acting in this direction. And so it turns out it would end up being 10 newtons of static friction. Well, now I'm going to stop there for a minute and just analyze the forces. If we could just isolate the forces acting on the ball right now, there's 10 newtons acting on the ball. The ball accelerates. Well, how about the person? How much is acting on the person? There's 10 newtons from the ball pushing back this direction, but there's also 10 newtons of static friction pushing back the original direction. And if you then calculate the net force acting on the person now, I don't think I want to do it that way. Okay, let's get that back here. Sorry. Get my arrow back here of 10 newtons. And that was static friction. If you looked at the forces acting on both of them, here and here, these are the two forces acting on the person. And so 10 minus 10 equals 0, and I don't move anywhere. Well, here we have a small problem. And the small problem is that there's no force right now going opposite of this 10 newtons, and there has to be, because for every force there's an equal and opposite reaction. So there must be 10 newtons pushing this way. Well, what is that 10 newtons pushing on? Well, he's standing on the earth, so there's 10 newtons pushing on the earth. Okay. Here's the deal. There's a net force acting on the earth of 10 newtons, and guess what the earth does? The earth accelerates a little bit this direction. So the earth does accelerate. And the ball is going to accelerate. So the earth accelerates, and so the ball accelerates and the earth accelerates. But here's the deal. The mass of the earth is huge. So it has a lot more inertia. So yes, it accelerates, but just a little bit, a little acceleration, whereas the ball accelerates a lot. So wrap it up. Basically, Newton's third law is followed, and you can see that being followed, where equal and opposite, and to figure out what happens to an individual or an object, you have to isolate the forces acting on the object. This has only 10 newtons acting on it, it accelerates. These right here have 10 newtons acting on the person in both directions. You get a net force of 0, he doesn't accelerate. There's a total of 10 newtons acting on the earth, so the earth accelerates, just not very much because it's got so much mass. All right, I hope that clears things up, or maybe I just muddied the water a little bit more.